My warm greetings to everyone. Thank you all for joining us today. I am Dr. Sangeeta Kasture representing Government of India. It is my pleasure to welcome you all for the side event on innovation for sustainable aviation fuel, jointly organized by Department of Biotechnology, Government of India, and Office of Energy Efficiency and Renewable Energy, Department of Energy, United States of America. Sustainable biofuels has been one of the 8 innovation challenges co-led by India, Brazil, China, and Canada. The IC4 challenge has successfully completed 5 years and has developed a strong knowledge base, policy understanding among the key members with creation of competent human resource and network of scientists across the globe. Sustainable aviation fuel are key to reducing aviation carbon emissions. However, presently, very limited SAF used due to several key challenges like higher cost, limited feedstock, and immature technologies. Through this collaborative platform, co-leads the US and India and key supporting members will provide solution to key challenges by enhancing feedstock base and developing newer and affordable technologies. Mission Innovation 2.0 provides unique opportunity to collaborate by exchanging knowledge, identifying key R&D needs, and convening funders. The launched collaborative platform Innovation for Sustainable Aviation Fuel (ISAF) is co-led by India and US with active support and engagement from key members China, Denmark, Netherlands, European Commission, and international agencies like International Energy Agency and ARENA. We are delighted to have participation of eminent speakers from various members, countries, and international organizations. It is privilege to hear opening remarks from Dr. Renu Swarup, Secretary, Department of Biotechnology, Government of India, and from Michael Beru, Deputy Assistant Secretary for Transportation, Office of Energy Efficiency and Renewable Energy, US Department of Energy. An overview talk on SAF will be delivered by Paul Durant, Arena, while country perspective will be provided by Mark from USA, myself and Dr. Anjan Ray from India, Dr. Eduardo from Brazil, Dr. Longalongama from China, Dr. Lassi Rosandi from Denmark, and Kees Kwan from Netherlands. At the end, Dr. Paulo Franchi from IEA, International Energy Agency, will share insights on potential for sustainable aviation fuel in a global net zero scenario. Thanks to MI Secretariat and host Chile for this opportunity and excellent support. With collaborative efforts, ISF platform will provide solutions for sustainable and affordable aviation fuels having a lower GHG footprint. Once again, I thank all the speakers for participating in the event. Last but not least, I would thank to my colleagues from India and colleagues from US for their valuable contribution for preparing this event. We look forward to successful collaborations through this initiative and for making successful sustainable aviation fuel. Thank you so much.
A very good morning, good afternoon, and good evening to all of you. It's always a pleasure to be a part of the Mission Innovation events. Today, it gives me immense pleasure to be here for this very important event, which is the side event of MI6, specifically for the IC4 platform, which is now moving into the innovations in sustainable aviation fuels as we move forward. It's very heartening to see that in the MI1, when we launched these missions, the IC4 platform was launched, which was on sustainable biofuels. And India was a key leader for this with all our other partners, China, Brazil, Canada, and participation of a number of countries. The innovation challenges themselves were a very important component of the MI 1.0. And these challenges have, over these 5 years, given us a level of confidence that we are now moving into the MI 2.0. MI6 holds great significance for all of us. It's a transition. We move into the next phase. It's a time for introspection to see how we did, and also time now to look at our future plans to see what is it that we would like to accomplish. The IC4 platform over these last few years has, as I said, very successfully been able to establish a very strong R&D base, connecting the researchers from different countries, helping us to build not only strengths in technology, but in human resource and infrastructure, and more importantly, connecting countries to a common goal. And that is, of course, the larger umbrella of the MI mission as we move together. The IC challenges, which were started, which were outlined with a lot of enthusiasm, with a lot of discussion, as I said, have given us an understanding in these years, how do we progress forward? In the sustainable biofuel challenge, collectively, the decision is that we make it more focused now on the aviation biofuel. Aviation biofuels poses huge challenges to us. It's not specific to any one country. It's a global challenge. And if the scientists and researchers, along with the industry and the startups, can come together and find technological solutions which can meet this challenge, it would be a great accomplishment. I'm confident that we will be able to do that. I'm also very pleased that India is taking on a leadership position for this as we move ahead. And also very, very happy to note that the US is now a co-lead with us in this, and we have the enthusiasm, the commitment, and the partnership for many of the MI members. That clearly goes to show that this is an important mission. The sustainable biofuels, which itself as a technology holds so much of promise in meeting the larger objective of our mission innovation, of not just enhancing our investments, but bringing out new technologies, cleaner technologies, which serve the good, that's a global good in the near future. Thank you all once again for being here today. I would like to compliment all the teams of all the different countries who worked so diligently in the first phase, and all those who have committed and agreed to be there for the second phase. A special thank you to the MI Secretariat, to the MI Steering Committee Chair, to my own team in India, my own team, Dr. Sangeeta Kusture, Dr. Tulli, Dr. Shams, the whole lot of them who worked so very hard. I can't take their names, closely with the Secretariat to see how we can achieve this initiative and move forward. I would like to reassure you, you have the fullest support of the Government of India. And as always, we look forward to your partnership to make this a success. Thank you very much. And I wish this event, this challenge, this next path that we are taking great success. Thank you very much.
Hello, my name is Michael Barabee. I'm the Deputy Assistant Secretary for Sustainable Transportation in the U.S. Department of Energy. I'm very happy to be joining you today to help with the relaunch of this very important mission. First, I'd like to thank the Clean Energy Ministerial and Mission Innovation for the opportunity to share some of our perspectives on decarbonizing transportation and the critical role that sustainable aviation will play. The Biden administration has established very aggressive goals to address the climate crisis that we are facing. We had mentioned on Earth Day our target to reduce emissions by 50 to 52% by 2030. Transportation is the largest source of CO2 in the United States inventory currently, and addressing transportation will be critical to meeting that goal and those beyond it as well. To achieve that goal, we're clearly going to need to use a wide variety of technologies, and we're going to need to address all aspects of the transportation system. There is substantial work going on road vehicles, both light duty and heavy duty. We are very proud of the work that we are accomplishing on reducing the cost of batteries and helping to accelerate the use of electrification in on-road vehicles. We're also working quite aggressively on hydrogen and fuel cell vehicles, which we think also will play a critical role, especially for those longer distance and heavier lift vehicles. But addressing on-road emissions alone will not be enough. Over 40% of the CO2 in transportation comes from vehicles that are not on-road vehicles. And aviation is the largest source of those, largest piece, and also the one that is projected to grow the most in the United States. That's why DOE is a proud partner and very happy to be joining our colleagues in India today in the relaunch of IC4, Innovation for Sustainable Aviation Fuel. Sustainable aviation fuel, we think, will provide a significant new opportunity for biomass in particular. We are very committed to looking at the over 1 billion tons of currently available biomass in the United States alone, looking from existing crops, from waste resources of all sort. We believe that we have the capability to supply the future liquid fuels that will be needed in aviation, maritime, and rail, sectors where electrification will not be able to be the primary source, most likely, of decarbonization. We currently have 3 very large-scale sustainable aviation fuel demo projects that are up and running, and that we hope to be producing fuel in the very near future. We're committed to help to accelerate the sustainable aviation fuel deployment through a combination of R&D that will be needed to help both reduce cost and identify new and additional pathways that can develop the fuel and do so in a very low greenhouse gas footprint. We are also very committed to the deployment and demonstration of new technologies to help de-risk the commercialization of new sustainable aviation fuels. We know the clock is ticking. Over the next 10 years, we must be doing the large-scale demonstrations, working with the private sector to de-risk the technologies, that by 2030, we are well on our path to having commercial activity and commercial plants producing sustainable aviation fuel in very significant volumes. That's the time frame needed if we really are going to achieve economy-wide decarbonization by 2050. So again, we're very proud to be co-leading IC4 and to be joining our colleagues in India on this very important initiative. And I wish you all the best today. Thank you.
Hello. It's my pleasure to be joining this session discussing a proposed new focus on biojet fuels under the Mission Innovation Challenge on Biofuels. Now, my name is Paul Durrant. I'm Head of End-Use Sectors and Bioenergy in the International Renewable Energy Agency, IRENA. If you don't know us, we're an intergovernmental organisation founded over a decade ago, and we work with our 164 member countries and the wider community to help them accelerate their energy transitions. I had the privilege of being involved in the establishment of Mission Innovation's Innovation Challenges almost 5 years ago now, and it's great to see that alongside the establishment of the new missions being launched this week, which are focused on wider societal challenges, some of the innovation challenges are continuing and evolving, focusing on addressing narrower but critically important barriers to progress. And by doing so, by bringing together key actors to share learning and plans and to create opportunities for joint working. So why a focus on biojet? My fellow speakers are going to be discussing aspects of biojet innovation in a lot more depth. I'll take the next 10 minutes or so to provide a bit of context on the wider energy transition and then how aviation and biojet fit within that. Now, in the context of more and more countries upping their ambition and committing to net zero targets, this year's edition of IRENA's annual Global Roadmap publication, our World Energy Transitions Outlook, focused on a pathway consistent with limiting global temperature rises to 1.5 degrees C and bringing CO2 emissions to net zero by mid-century. We published key findings of that in March, and the full report is coming on the 16th of June. Now, that goal of 1.5 degrees is a step beyond our previous analysis of well below 2 degrees. And whilst the direction of those two scenarios and the building blocks are the same, the pace and scale are notably larger and faster across all aspects of the energy transition. And if we're going to have a fighting chance of delivering that high ambition, we're going to need innovation to accelerate the pace, reduce costs, remove barriers in multiple parts of the energy system. And we're also going to need closer international cooperation so that the solutions work for all regions of the world. The chart you're seeing now shows us how the use of key energy carriers evolve over time in IRENA's 1.5 degree scenario. Renewable energy supply, electrification, and energy efficiency are the key components of that transition. And our analysis suggests that we have most of the technologies that are needed for that transition. And crucially, that energy transition is affordable. As I said earlier, the pace and scale, however, is daunting. To give you a sense of that, by 2050, power generation triples compared to today's level, and renewable supply reaches 90% of total electricity, up from 25% in 2018. That's going to require 10 times more renewable power generation capacity. By 2050, around 58% of final energy consumption is electrified, either directly or through green hydrogen and its derivatives. And hydrogen demand grows from 120 megatons to 613 megatons in 2050. That requires something like 160 gigawatts of electrolyzers to be added every year from now to 2050. Installed capacity of electrolyzers was 0.3 gigawatts in 2020. Biomass equally needs to substantially grow. In the 1.5 degree scenario, it grows sustainably from 54 exajoules to 153 exajoules in 2050, with biomass and its derivatives accounting for 18% of final energy use by 2050. Now, that 153 exajoules is at the high end of our and others' assessments of sustainable potential. One of the big challenges in the energy transition, therefore, will be scaling up production sustainably, i.e. without causing social, environmental or economic harms. Now, that's not a new insight. We've known that for many years, and people have been working on that for many years. But 1.5 degrees C and net zero goals increases the urgency and scale significantly. Ensuring we can deliver that order of magnitude increase is going to be complex. Now, let's focus in on aviation. Aviation is widely regarded as one of the trickiest sectors to decarbonise. Globally, aviation produced 915 million tonnes of CO2 in 2019. It's about 2% of total global emissions. And it was a sector that is expected to grow. Prior to the COVID-induced reductions, annual jet fuel consumption was about 360 billion litres a year. And it was forecast to more than double by 2050. As with other sectors, as other sectors decarbonise fast, aviation will account for a growing share of remaining emissions. And beyond energy use, aviation also is responsible for non-CO2 related impacts on the climate. The industry is committed to a 50% reduction in CO2 emissions by 2050. But in the context of those global net zero targets, 50% reduction is not ambitious enough. IRENA's 1.5 degree scenario suggests aviation emissions will need to fall by about 90% by 2050. Now, the optimum mix of solutions to decarbonise aviation is still not clear at this point in time. However, the key building blocks are pretty clear. As with most sectors, the starting point needs to be to manage demand, both in terms of demand for air travel and the energy demand of that travel, i.e. by improving efficiency of aircraft and of operations. Beyond that, we have only a small number of possible solutions. Firstly, the replacement of fossil-based jet fuel with so-called sustainable aviation fuels, SAFs. These are fuels that have significantly lower emissions, but which are sufficiently similar to jet fuels to be drop-in replacements, and they don't require major changes in aircraft. Two options here. Firstly, biojet, focus of today's discussion, which we'll come back to, or the production of synthetic kerosene. Beyond that, our other options are the direct use of hydrogen or the direct use of electricity supplied by batteries. Now, energy density considerations mean battery-powered aircraft will have a role, but it will likely be limited to short-haul flights and small aircraft. Hydrogen, by contrast, has a high energy density, but it also has a high volume, and its direct use will require completely new aircraft designs and propulsion systems. In common with the excitement about hydrogen in other parts of the energy system, there are developments underway for the use of hydrogen. Airbus, notably, is exploring the development of a number of aircraft designs, which they hope to have in commercial operation by 2035. Remains to be seen how those technologies will develop, but even in the most optimistic scenarios, they'll only start to have a real impact in the 2040s, and their use will likely be limited to mid-range flights and mid-sized aircraft. So from that, we can see that it's sustainable aviation drop-in fuels that will be essential in the short to medium term to start driving down emissions and will likely still play a major role in 2050. Briefly to talk about synthetic kerosene, produced from clean, preferably green hydrogen. It's a valid option that will scale over time. However, currently synthetic jet fuel is only in some cases within certified pathways, and current production is highly limited due to high costs and challenges in sourcing both green hydrogen and clean CO2. So let's talk about biojet. Biojet looks to be the only cost-effective option for partial emission reductions in aviation in the next decade, and it looks likely to play a major role in decarbonisation through to 2050. Our 1.5 degree scenario assumes that energy demand can be held down so that only increases slightly by 2050. And within that scenario, biojet fuels provides roughly 50% of final energy demand. Delivering that level of energy demand would require about 200 billion litres of biojet fuels per annum in 2050. Next month, as a part of a series of deep dive reports on key components of the pathway to zero, we will be publishing the Reaching Zero with Renewables briefing paper on biojet fuels. That explores in depth the current status and future potential of biojet and the actions needed to realise that potential. Let me give you a few insights from that work, and then I think other presenters will dive a little deeper. Current biojet production is about 140 million litres per year. And although production has increased significantly, it's up from 7 million litres in the previous year, commercial volumes remain relatively small, less than 0.04% of current aviation fuel use. Production is currently limited to 2 plants that routinely supply about 9 airports, and whilst demand is ticking upwards, biojet use is still relatively low. It's typically blended in low ratios with fossil jet fuel, and cumulatively to date, an impressive sounding 315,000 flights have used blended biojet fuels. But that's less than 1% of flights in 2019. To date, 8 pathways have received the official certification necessary to allow biojet fuel to be blended with petroleum-derived jet fuels or co-processed. However, the vast majority of biojet fuel is currently produced via one major route, via the hydrotreatment of fats, oils and greases, so-called FOGs, such as used cooking oils. These oleochemical lipid feedstocks are also known as hydrotreated esters and fatty acids, HEFA, or hydrotreated vegetable oils, HVO. So those terms are often used to describe the primary route for production of biojet at the moment, HEFA or HVO. Our report highlights ways in which existing production can be expanded to circa 1 billion litres per annum relatively easy. Beyond that, we assess the potential biojet production based on the estimated volumes of economically accessible used cooking oil could reach somewhere between 3.5 and 12 billion litres globally. though some estimates go much higher and estimate as much as 100 billion litres, we think it is a lot lower than that. To significantly scale up production beyond what used cooking oil can offer, we're going to need alternative feedstocks such as lignocellulosic biomass and alternative technologies such as gasification with Fischer-Tropsch, pyrolysis, or hydrothermal liquefaction. Now, these next generation biofuels could in principle be derived from more available biomass substrates such as agricultural or forestry effluents, wastes and residuals, and maybe even algae. Although it's likely that these routes can deliver in the medium to longer term, neither the technologies nor the biomass supply chains are yet well developed. So this is where further innovation really needs to kick in. Finally, a quick word about costs. Fuels produced by the HEFA HVO route cost around between 3 and 6 times more than conventional jet fuel. And that's mainly due to higher feedstock costs. High capital costs will be an obstacle for some of the other technologies that I mentioned, such as gasification. Our report highlights various strategies focused on that, but the cost disparity will remain for many years to come and will require policy interventions, but is also a powerful driver for innovation. So in conclusion, as with other parts of the energy system, global goals of deep decarbonisation by 2050 require concerted action this decade. Aviation is one of the sectors where least progress has been made. Biojet has a crucial role to play in addressing that and has significant potential. But we need systemic innovation, including technology innovation in feedstocks and conversion technologies, but going beyond that, where technology innovation goes hand in hand with innovation in supply chains, business models, and the financial and policy incentives. Together, that systemic innovation can greatly increase the future prospects of biojet fuels. Looking forward to the presentations of my colleagues. Many thanks for your attention.
My warm greetings to all. I am Dr. Sangeeta Kasturi, representing Department of Biotechnology, Ministry of Science and Technology, Government of India. Department of Biotechnology, known as DBT, has been promoting innovations and research development and demonstration through multiple schemes at both national and international level. It is my pleasure to present India's perspective on sustainable aviation fuel for the side event of 6th Mission Innovation Ministerial. Thanks to Mission Innovation Secretariat and Chilean host for giving this opportunity. India has been engaged actively in MI activities and was co-leading sustainable biofuel innovation challenges along with countries Brazil, Canada, and China. Few collaborative projects supported by India in advanced biofuel areas, including the jet fuel R&D. Building on success of R&D base during phase 1, co-leads have agreed to work together in focused areas of sustainable aviation fuel. Liquid biofuels is one of the prime candidates for decarbonization of hard-to-abate transport sector and thus can result in substantial reduction in the GHG emissions. The National Policy on Biofuels 2018 encourages blending of biofuels in conventional fossil fuels. Aviation fuel consumption in India accounts for about 8% of Asia's aviation fuel demand, with average annual growth in the range of 7 to 9%. Current production of aviation fuel is 180,000 barrels per day, though COVID pandemic has adversely affected consumption of aviation fuel. Meeting ASTM specification is extremely important for SAF. Once certified, SAF can be used for blending purpose in aircraft using an airport delivery network. Aviation presently contributes 3% of global GHG emissions. A significant increase in the production and consumption of sustainable aviation fuel is required in order to achieve the GHG emission reduction targets proposed by ICAO. Presently, less than 0.1% of jet fuel is from bio-origin and 99% of this is hydroprocessed esters of fatty acids. Feedstock plays very important role. GHG reduction potential differs depending on the raw material used with respect to conventional jet fuel. A concerted efforts required along the value chain, hence it is important that all sectors and concerned ministries work together. DBT, Ministry of Science and Technology, promotes innovation and RD&D by funding projects, while Ministry of Petroleum and Natural Gas regularly work on policy and implementation aspects. CSR labs, DBT bioenergy centers, NGOs, institutions like IITs, universities all implement R&D projects. Oil marketing companies produce large SAF quantities from a viable refinery-based technology. The Ministry of Civil Aviation is interested in meeting the forthcoming ICAO regulations for low GHG emissions from aviation sector. Sustainable supply of feedstock is most important part for commercialization of SAF. Currently, used cooking oil is used. About 10% of edible oil is available in India of volume around 2 million tons per annum. Tree-borne oils have certain challenges on supply side with respect to yields, harvesting, etc. Hence, the potential feedstock would be short rotation non-edible oilseed crops of mustard family, for example, Niger, Carinata, camelina, etc. Jatropha oil has been successfully converted into SAF at pilot scale by CSR, Indian Institute of Petroleum. The biojet fuel produced by this method meets ASTM specifications and has been tested successfully in commercial flights. Following my talk, Dr. Anjan Ray, who is director of IIP, will briefly talk about the success story on biojet fuel. For sustainability, it is always important that multiple feedstocks are explored for SAF and innovative and cost-effective pathways are developed. A few examples of low carbon pathways are alcohol to jet technology coming from cellulosic sugars, catalytic hydrothermal liquefaction, microbial conversion of alcohol to isobutene, that is again from sugars, syngas from biomass as well as municipal solid waste, that is through gasification, then the clean polymerization, direct reduction of CO2, that is power to liquid, and microbial lipid production. Life cycle analysis of these pathways is very important. As mentioned earlier, GHG reduction potential of SAF vis-a-vis petrofuel depends on feedstock type as well as technology pathways. Into power to liquid pathways, there are huge opportunities in India for production of clean liquid fuel using renewable power, hydrogen and carbon dioxide. Various R&D segments are electrolyzer design, catalyst development, carbon dioxide capture, reduction, etc. Primary objective of ISAF is need of sustainable feedstock and cost-effective pathways for scalable production of aviation fuel. Hence, through this collaborative platform, it is expected that the R&D efforts members can demonstrate technologies and share knowledge and best practices. Look forward to closely work with co-lead US and other supporting members. In conclusion, I would reiterate that scalability and delivered cost are the primary challenges. For SAF, net energy ratio, LCA studies, techno-economic analysis are very important at early stage. Collaborative efforts are key to speed up technology development. and a deep engagement of stakeholders supported by conducive policies and R&D efforts will make a difference. Mission Innovation is a uniquely placed opportunity to undertake this challenge. Together, let us keep our skies clean and beautiful. Thank you so much. I can be contacted at given email ID sangeeta.kasture at nic.in. So again, thank you so much for your attention.
Good day to you. On behalf of the CSIR Indian Institute of Petroleum, Dehradun, it is my privilege to present to you the latest activities towards commercial deployment of sustainable aviation fuels in India. At our institute, we have been working on this for a decade and a bit more. This culminated in a civilian flight of a Bombardier Q400 turboprop on Pratt & Whitney engines in 2018 August, followed by a range of military flights on the Antonov 32 Russian turboprop transport platform since 2019. Our sustainable aviation fuel process is similar to the globally established HEFA process, but it has lower capital and operating costs, and it has been running since January 2018, almost continuously, and providing ongoing supplies to the Indian Air Force. We are currently in discussions with a refinery major as well as an engineering major to build a demonstration plant of about 15 tons per day. This is also required for the qualification of the fuel through the ASTM D4054 process. We plan to use feedstocks which are available abundantly today, like used cooking oil and palm stearin, but also tree-borne oils and rotation crops and futuristic feedstocks that we believe can be brought to scale in India through the supply chain aspects of the research. Aviation biofuels have taken longer than we hoped to reach where we have reached, but we think we will get there soon enough, propelled by international activities like CORSIA and with concerted efforts along the value chain, with deep engagements of stakeholders and policymakers and passionate researchers like we have on our campus. We hope that our future will be sustainable and that we will be able to give back more to nature than we have taken from it all these days. Thank you.
Hello, my name is Mark Schmorhan. I'm a technology manager with the Bioenergy Technologies Office at the Department of Energy. I'm pleased to provide the U.S. country perspective on sustainable aviation fuels. I would like to thank the Clean Energy Ministerial and Mission Innovation for the opportunity to share DOE's perspective on decarbonizing air transportation in the United States. Air travel is expected to nearly double by 2050, and jet fuel consumption accounts for 8 to 12% of domestic emissions. The U.S. consumes approximately 26 billion gallons of jet fuel, and there are limited prospects of commercial flight electrification. Current SAF production in the United States is limited, and it does compete with renewable diesel. SAF is currently produced by hydroprocessing fats, oils, and greases into drop-in hydrocarbons, also known as the HEFA process. HEFA for SAF competes with HEFA for renewable diesel, which has a larger market in the United States. HEFA refining capacity in the US is growing, but those processes that rely on waste fats, oils, and greases will be constrained to supply chain limitations of waste fog. In the US, SAF capacity is growing over the next 3 to 5 years, as indicated by the various corporate announcements on this slide, and it will expand us beyond HEFA into new feedstocks, including lignocellulosic biomass, alcohol, municipal solid waste, and forestry residues. The US airline industry has made significant commitments to net zero carbon emissions by 2050. As part of that commitment, they've pledged to work with governments and other stakeholders to rapidly expand production and deployment of SAF in the US with a goal of making 2 billion gallons of SAF available by 2030. There's also proposed legislation in the United States to incentivize the production of SAF. Currently, under negotiation are blenders tax credits, investment tax credits, and other grant programs. Several federal agencies have coordinated their SAF efforts across the supply chain, from feedstock, production and logistics, to fuel conversion, to scale up, to fuel testing and production, and the end users. So those various stakeholders are indicated on this slide. BETO has conducted several workshops that focused on understanding the technologies available for scalable production, their economic competitiveness, their environmental benefits, and the supply chains for feedstocks that would enable biofuel jet deployment. These workshops have informed our current investments in SAF. DOE is developing multiple SAF pathways, as shown on this chart. And our portfolio today consists of approximately $200 million in federal commitments for process technologies across various maturities, from R&D through demonstration scale, and that will consume feedstocks ranging from biomass to ethanol to fats, oils, and greases. In fiscal year 21, BETO announced a funding opportunity announcement for $31 million to focus on the development and demonstration of low-carbon biofuels for aviation, marine, and heavy-duty markets. Those technologies must deliver a 70% greenhouse gas emissions reduction, and they're available for technologies at various scales, from pre-pilot unit operations through demonstration scale facilities. Thank you for your attention. I look forward to joining India as co-leads as for IC4, the Innovations for Sustainable Aviation Fuel. And we look forward to working with other member countries and stakeholders on growing the sustainable aviation fuel supply and markets. Thank you so much for your attention.
I'd like to first thank the organizers for the opportunity to say a few words about sustainable aviation fuels in Brazil. And we can start by asking a question. What is the global production of biofuels today? And the number is between 3 and 5%. When you look at the biofuels share of the internal demand of fuels for transportation in Brazil, one reaches 23% on an energy basis, which corresponds to about 30% on volume. How did we get to this? It took us nearly 5 decades, the graph shown on the right. In green is the ethanol production since the oil crisis, all the way up to 30 billion liters a year. And then you have biodiesel in excess of 5 billion liters a year. The take-home message from this slide is that it took probably at least a decade for us to reach 10 billion liters of biofuel in ethanol, and will take 15 years or so to get to the same level for biodiesel. So the question is, how long will it take for us to do that in biojet fuel, knowing that the carbon offsets targets are out there for 2027. So let's have a look at what the eligible fuels are that Corsia is putting forward. These are the life cycle emissions. So the green line on the red line on the top has to do with the fossil fuel. The blue bars are the core LCA values. The green bars correspond to indirect land use change. And here I call your attention that when you're calculating ILUCs, one must investigate country-specific data so that you can properly take into account the indirect effects that exist between the different economic sectors. The circle, black circles, has to do with the sum of both. And on the bottom here, you see that Brazil has about 5 certified routes in the country. Fat acids, 2 of them here, alcohol to jet, another 2, and then synthesized isoparaffin at the end here. But notice that there are global routes that could actually be of interest to Brazil. Should call your attention that they don't have green bars because they mostly depend on residues. And we have a large project in the nation trying to address that. This is a consortia called BioValue that involves 11 universities and research centers, and also partners from industry, from aviation, oil and gas, and pulp and paper sectors. This is a Horizon 2020 project that has a sister project in Europe called Be Cool, and among other things is trying to integrate biochemical and thermochemical routes as well in the typical biomass to liquid strategies. An outlook for the future, we think we should not discard technologies. On the contrary, we should explore as many as possible. We know the drawbacks from fossil fuel routes, which are high temperatures and pressures, heavy metals, and high hydrogenation inputs. And we think that biochemical routes have the opportunity to be more efficient, specific, customizable, and obviously environmentally friendly. And this is a potential area for international collaboration as well. Well, in summary, I believe it will take at least a decade of continuous R&D and country-specific policies so that we can have biojet fuel at a reasonable production scale in Brazil. That R&D should be accompanied with scaling up capabilities, and we should not discard, but rather consider different types of technologies and routes. And finally, continuous financial support is necessary so that we can foster partnerships between industry and research centers, and obviously international collaboration. So I'd like to thank you very much for your attention.
Good morning, ladies and gentlemen. I'm Longlong Ma from Guangzhou Institute of Energy Conversion, Chinese Academy of Sciences, Chief Representative of China MI-SE4 team. It is a great honor to give a brief introduction of sustainable aviation fuel development in China. This presentation includes 4 parts. As it was announced lately, China aims to reach CO2 emission peak before 2030 and achieve carbon neutrality before 2060. Under the dual carbon target, CO2 emission reduction in aviation industry is facing great challenges. Several policies have been formulated by Civil Aviation Administration of China, also called CAAC, to address green growth of aviation, such as 13th 5-year plan for energy conservation and emission reduction in civil aviation, and the guidelines on force enhancing green development in civil aviation. Chinese government has always attached great importance to the development of biomass energy, especially the key technology research and the industrialization of bio-liquid fuels. It is aiming at the marketization operation and mandatory blending to always new production routine explanation. The promotion is shifting from government to industry role. According to the CAAC's policies, by 2035, the concept of green development will be deeply rooted in the whole industry. The Green Development Policy System, Standard System, and Assessment System will be mature and complete. The green management level will be greatly improved. To achieve these green aviation goals, China will further implement the carbon emission trading mechanism, introduce more active social support policies, encourage aircraft to use more alternative fuels and additives, and promote SAF airworthiness certification. Current technology allows SAF to be produced from a wide range of feedstock, including crop, straw, forest residues, and agricultural residues, and urban household waste. The other sources, such as algae, could also be used for SAF production. Besides, using the waste gases produced as a byproduct in steel manufacturing to produce SAF is showing great potential. Overall, there is at least 1.5 billion tons of feedstock available for SAF production in China. Currently, the annual aviation consumption in China is about 36.9 million tons per year by airlines. As to the SAF, the expected demand will be 5 million tons per year if 10% of jet fuel is supplied by the SAF in 2025. Therefore, the development of SAF will bring great advantages to sustainable development goals for the various aspects. Over the past 5 years, remarkable achievements were made in the construction of aviation infrastructures. Let me take the total investment from 2016 to 2018 as an example. More than 8 billion yuan of investment is used to conserve aviation energy and reduce carbon emission. 65% of the investment is in the field of technology innovation, including the promotion of SAF R&D. More concretely, these promotion measurements are reflected in the following aspects. 1. Purchase agreement with the SAF suppliers. 2. Investment and significant start-up spots for SAF projects. 3. Pioneer airports with the regular SAF supplies, and support the testing flights with SAF. In addition, the large-scale SAF pilot construction has been highly concerned and supported by several national departments in China, including MOST, MOA, and others. The R&D of APC technology from lignocellulose biomass, led by our institute, has achieved great success. And 2,000 ton per year demonstration projects are under construction. The system energy efficiency can reach 36.8%, and the fuel quality meets the ASTM D7566 standard. The production cost is about 9,000 to 10,000 yuan per ton, which is half cost of grease technology. As a conclusion, to tackle climate change and the international regulation of aviation emission, the following aspects we will enforce in the next step. 1. Improve middle and long action plan for SAF development. 2. Take primary responsibility by airports and airlines. 3. Attract private investment and improve policy system. 4. Intensify the integrated industry chain. 5. Enhance international communication and cooperation. That's all. Thanks.
Thank you for this opportunity to present the Danish roadmap to sustainable fuels. My name is Lasse Rosendal. I'm the head of the Department of Energy Technology at Aalborg University in Denmark. The Danish greenhouse gas reduction targets follow 3 levels. In 2025, 50 to 54% reduction. In 2030, 70% reduction, and by 2050, full carbon neutrality is envisaged in our emission profile. You can see in the graph to the right that as we go towards 2030, the 70% target lies a bit beyond what we can bring about by known technologies already today. So there is obviously a research challenge for us to reach the 70% target in only 9 years. The way the Danish government has gone about this is to set up 4 green missions, one on carbon capture, storage and use, one on green fuels, one on sustainable agriculture, and one on recycling and reduction of plastic waste. In the Danish Center for Energy Storage, we've coordinated a draft roadmap for the green fuel mission based on inputs from more than 100 stakeholders. And the essence of this roadmap is obviously, as a roadmap focusing on the entire transport sector. It's quite diverse, so it has a number of energy sources, intermediate energy carriers and technologies before we get to a wide range of final products. So it's across all transport modes. It's both biofuels and power to X and combinations. It's carbonaceous and non-carbonaceous fuels, so it is very much a diverse pathway leading towards a range of sustainable transport fuels in the future. If we focus on jet fuel, it's a little less crowded. On the graph to the left, you can see the expected consumption by fuel type in 2020, 2030, 2050. And as we look towards 2050, we can see that the consumption is very much dominated by kerosene, by jet fuel. There is a small amount of hydrogen now also in the mix, and also a small amount of electrically powered aviation. So that obviously means that the roadmap is dominated by different types of conversion technologies, where we work with a number of different biomasses and organic waste inputs, convert them in a number of stages, mostly towards jet fuel. And all of this is then combined with green hydrogen. So back to this comment that we have not both pure biofuels, but also the combination of green carbon from a biomass and green hydrogen from a power to X implementation. In Denmark, we are predominantly looking at gasification to form a syngas, and then followed by either Fischer-Tropsch or other types of synthesis, biogas, where subsequently we create a syngas and then go through methanol to create jet fuel, and then bio oils, either pyrolysis or hydrothermal liquefaction, that are then refined to produce a kerosene. So we have these in scope, these different types of technologies. To give an example of where Denmark stands in terms of research, I've selected very recent jet fuel results from hydrothermal liquefaction that we've achieved in a European project, the Horizon 2020 project. So HCl jet fuel based on sewage sludge. You can see the distillation curves to the left. If you then take the jet fuel, the distilled jet fuel cut, and carry out a much more detailed analysis in terms of aviation fuel properties. This has been done by DLR within the JetScreen project and also University of Dayton Heat Lab. You can see how this potential SAF performs compared to a conventional jet fuel. You can see in the distillation curve to the right, the green area is conventional jet fuel. The black line with the dots is the HTL jet fuel, and you see that it's very close and definitely within specification limits. You can see moving just a tad to the left, you see the small bar plots. You see the black dot, which is the HCl fuel, lies very well within specification limits, and in most cases actually within normal jet fuel range. And the final one you can see is the distribution of carbon numbers, very much similar to a regular jet fuel. And you can also see that in terms of the average carbon number, this jet fuel is 11.3, whereas on average fossil kerosene is 11.4. So very, very close, and it very much indicates that there is definitely a whole range of bio-derived jet fuels that can be brought into play in the future. So to sum up, in terms of the Danish ambitions, based on the roadmaps that were produced here in the spring, delivered on May 12th, there will be a call to distribute 100 million euros onto these 4 green missions. This call will open in August, and there'll be a decision in December 21 as to which activities we'll go forward with. And as I said earlier on, there'll be a focus on near-term implementation and longer-term research targets. In terms of Danish strongholds, it's distributed across different technologies, either liquefaction technologies to produce an oil and then refined to a jet fuel. An example of an ongoing project is what's called the Low Carb Fuels Project that focuses on this. We have gasification and Fischer-Tropsch as a pathway, and then based on the very large biogas stronghold in Denmark via methanol and CO2 to produce a jet fuel. So this is the range of technologies that we'll be focusing on. One further thing in terms of Danish competences is sector coupling, understanding how to link these green fuel technologies with, for example, the carbon capture activities, but also sustainable agriculture, and to exploit the links across different energy vectors, so to really make an efficient integration. Another stronghold lies in the types of projects that are hosted in Denmark. For example, Copenhagen Airport leads the European Alight project as a lighthouse airport, and is a project where we are focusing on how to integrate, how to implement sustainable practices actually within the airport itself. The last point to be made is that, as you can see on this chart, that plots in a number of relevant technologies in terms of TRL. It's quite clear that in order to actually meet both 2030 and 2050 targets, that there is quite a significant amount of research that needs to be done in order to advance those technologies that lie in the low TRL all the way to the high TRL to 8 and 9, where we are going into demonstration and scale-ups in order to really implement. So it's important that the funding instruments both facilitate the implementation, but also the research that advances the technology field as a whole. And on only left for me to say that if you are interested to hear more about the Danish outlook, there are some contact infos here on this slide. And other than that, I'd like to thank you all for your attention. Thank you very much.
Good morning, good afternoon, good night. My name is Kees Kwant from the Netherlands Enterprise Agency, Department of the Ministry of Economic Affairs and Climate. And from the Netherlands, I'm involved in mission innovation, IC Challenge 4, where we look into biofuels, but also into sustainable aviation fuels. We are very happy that we will now start a new extended collaboration on aviation fuels, and I will explain to you what we are doing in the Netherlands on aviation fuels. Aviation fuels in the Netherlands are important because the Netherlands is looking for a major greenhouse gas reduction. In the year 2050, we tried to achieve 0 greenhouse gas reductions, and 4 years ago, a climate agreement has been formulated to realize in the year 2030 already 49%. This actually, because of the Green Deal in Europe, will go up to 55% very soon. So all sectors in the Netherlands have to contribute to this. So it's a total emission from the Netherlands has to be reduced. So it's about buildings, it's about electricity, it's also about the industry sector and also mobility. So for all these sectors, we have developed plans and they are being implemented right now. However, if you look here, you can see that, for example, in the mobility sector, we have introduced biofuels. And at this moment, we have an increased amount of biofuels. So it has gone up to about 5%, and it's now even higher with, let's say, percentage of biofuels in the Netherlands. And we mainly use ethanol to replace petrol. We use some biogas, so, and also a little bit HVO, but it's mainly FAME that is used to produce the diesel. So all these different biofuels play a role. But of course, we are now also asking ourselves the question, this is in road transport, but what can we do in aviation? So for aviation, we have formulated an action program on aviation fuels. And in this program, we have formulated a goal for 2030 of 14% sustainable aviation fuels. We think that up till, let's say, the year 2030, we will mainly work with HEFA, but we will also develop new fuels, advanced biofuels, advanced aviation fuels that can be used and that can be approved by the ASTM. So all these new fuels will play a role. And so recently we have developed a European high-level conference on sustainable aviation fuels. And there you can hear our minister and also other ministers talk about this ambition and also what needs to be done. But in Europe, we are very serious about this 14% of greenhouse gas reduction in the aviation sector and go up to at least 50% in the year 2050. But we need innovation to make this happen. So up till now in the Netherlands, we have had a system, it's called the transport support. But this year, in 2021, we will have two new, let's say, calls. And there is one specific call for aviation and marine biofuels. I will explain more to you about that a little bit later. But also as a follow-up of the climate agreement, we have a national call for the mobility sector. There is a lot of money involved, 150 million euro. And there all the different options are included. So from sustainable biofuels, also to e-fuels, including methanol. And we will really have to see how we can make the mobility sector more sustainable. For this specific call on aviation, the call will open on the 6th of July of this year in the Netherlands, and the closing date is 14 September. There is a subsidy of 3.36 million euro available, and the maximum subsidy for each project is 500,000. So we can finance about 6 to 7 projects from this fund. The requirements are that we in each project, we want to see at least one company in the consortium. We will fund research institutes, we will fund industries that develop innovative and sound technologies. And we encourage all these people who develop a project to look for collaboration with partners from other countries through the Mission Innovation Force. So I'm looking forward that we in the coming future, we can organize matchmaking between Dutch entrepreneurs and researchers and also from other IC4 countries. So you can find here the link to the call that will show you what is happening there. So if you want more information, you can send an email. Thank you very much for your attention. This was my short introduction to the IC4 contribution from the Netherlands. Thank you very much.
Good morning, good afternoon, ladies and gentlemen. My name is Paulo Frankel. I'm the head of the Renewable Energy Division at the IEA. First of all, I would like to thank the government of India and the United States for the opportunity to speak at this important topic of sustainable aviation fuels. Over the next few minutes, I will share the results of the IEA's landmark net zero emission analysis and the role of that sustainable aviation fuels will need to play in supporting a global net zero emission trajectory. On May 18th, the IEA released the world's first comprehensive energy roadmap to meet net zero emissions by 2050. A roadmap means not just targets, but also a concrete set of measures to be taken to get there. We consider in our analysis more than 400 milestones to guide the global journey to net zero by 2050. And without going too much in detail of this figure, I would like to highlight that today, many of the solutions up to 2030 exist relying on commercial technologies. So for instance, the power sector goes net zero by 2040, and 60% of global car sales are electric by 2030. But after that, new and emerging technologies will be needed, in particular in hard to abate sectors like long distance transport, aviation, and industry. So sustainable aviation fuels is one of such important technology pathways. And according to our analysis, half of the fuels used in aviation must come from sustainable sources by 2040. This is a huge increase from the 0.1% of today. Now, over time, biofuels actually shift to aviation. They have to grow, they have to triple in transport, going up to 11% of total transport energy demand by 2030, and then further to 14% by 2050, even when as electric vehicles and hydrogen expand. Today, nearly all liquid biofuels are used in road transport, and we expect that to continue to expand to 2030. However, in the longer term, as other alternatives such electric and hydrogen vehicles displace some combustion vehicles, liquid biofuels shift to aviation, which has fewer alternatives, reaching 55% of the total by 2050. For sustainable aviation fuels to play this role in net zero, they must start production at scale in this decade and then continue to expand in 2050. Now, if you compare the different uses in the transport, indeed, sustainable aviation fuels have the smallest share of mature technologies. Most of the technologies are in the prototype or demonstration phase, and this includes indeed many sustainable aviation fuels technology pathways. Some biofuels in the form of biojet are just entering the market uptake phase today, but many other technologies needed to be demonstrated and then scaled, and this is the obvious important topic of the proposed innovation challenge. Now, looking more carefully about advanced biofuels, the world can, this is one important path with which the world can expand bioenergy at scale while minimizing the impacts on the environment. Today, most liquid biofuels come from conventional ethanol and biodiesel, with a large share produced from crops like corn, sugar, wheat, and soybeans. Over the coming decade, advanced biofuels that have both low carbon intensity and don't compete with food or forest land use grow considerably. So by 2030, as you can see in this graph, advanced fuels make up 45% of total biofuel production. This is the challenge. To move the world onto this pathway means expanding advanced fuel production from near zero today to an industry larger than the total liquid biofuels industry today in less than 10 years. This is the huge challenge that we have to address in this decade. Succeeding in this challenge means taking bold but affordable steps. In 2030, 15% of aviation fuel come from sustainable sources, almost all from biojet. In 2050, 75% of total fuel consumption comes from sustainable fuels, 45% from biojet, and an additional 30% from hydrogen. Now, these are all nice numbers, but they will not come by themselves. First of all, the challenge already in 2030, 15% of the share means is equivalent to expand sustainable aviation fuels by 6 average size production facility per year, every year to 2030. This needs to come from two levels that are very the focus of this initiative: innovation, by de-risking investment, expanding financial support for research, expand first-of-its-kind commercial facilities and demonstration plants, and increasing use of waste feedstocks and carbon capture and storage to maximize the environmental benefits. The second focus of the Mission Innovation Challenge is international collaboration on two levels: share learnings, fundamental, share results of research, demonstration, deployment, and remove roadblocks in order to collaborate to strengthen supply chains, infrastructures, international standards, and manage the obvious competitiveness impacts and avoid unintended impacts. Now, these are the two most important focus level of the mission innovation. I wish to remind us these needs to remain consistent with demand signals. And demand signals is government policies that can encourage a sustainable aviation market with some earmarked targets, also profiting and exploiting economy recovery packages as appropriate, introduce regulations, consider incorporating carbon pricing where appropriate, and then also, however, signals from industry, setting internal targets, voluntary actions, long-term sustainable aviation fuel contracts, just as an example. All this will need massive action now in order to deliver to 2030 and then prepare for the longer term benefits by 2050. I thank you very much for your attention. Thank you.